Now the next thing which is coming up now is second order gradients. You already know first order gradients, like derivative of the loss with respect to x. There are some cases where you can actually take the derivatives multiple times. So like, if you want to take the square, if you want to take the derivative once again, then it will be derivative of the square of the loss with respect to x square. And if you want to take it with respect to y, then it will be derivative of the loss with respect to y square. So these are all second order derivatives. So now this exercise is actually dealing with how to calculate the higher order derivatives. Earlier case or earlier exercise was only calculating the single order derivatives, which are derivative of the loss with respect to x or with respect to y. So now in this particular piece of code, we are actually implementing the higher order derivatives. So here you see the particle position is given as 5t square plus 7. So if I take the derivative of this position with respect to time, what I am getting is velocity. And if I take again one more derivative of the position with respect to time, what I will get is acceleration. So here the velocity is 10t and the acceleration will be 10. So let us run this particular piece of code and see what we will get if you use the gradient tape. So here you see in this particular case, I am using the nested gradient tapes. First gradient tape is defined as outer, the second gradient tape is defined as inner, and this is the position which I have already defined. So speed actually is defined as the derivative of the inner tape gradient with position with respect to time, and then for the acceleration, this is acceleration actually, not velocity, and this is velocity here. So now once you so basically this will be velocity and this will be acceleration. So now if you calculate this particular piece of code, so what exactly this particular piece of code is implementing this derivative, and this particular piece of code is actually implementing this derivative, which is the double derivative. And then we will run and see whether the answers are right or not. So here, and then answer is 30 and 10. As you can see over here, we were getting that same answer. So here the time is actually 3. So this answer will be 30 and the acceleration is 10. So you can see both answers are same. And now what we are able to do is you can calculate the higher order derivatives by using the nested TF dot gradient tapes like this. Other way of defining this is or you can say other way of implementing this is you can use persistent equal to true, and then you can run this particular piece of code and you will get the same answer. So you can see both the answers are same. So now this actually covers up the majority of the concepts that are required for TF dot gradients. In the next exercise, what we are doing is we are defining a function which is actually a function of two variables x and y here, which is defined like this. And I'm actually using TensorFlow to find the minimum of this function using gradient descent. So it's very easy to do it. So what you do is you actually use x and y, and these are the variables. You are initializing them with 0 value, as you already know. And then I'm defining this function like this. Here you see it's just an implementation of the same function, and I'm calling it as f underscore x. And then what I'm doing is I'm actually calling the optimizer Adam here by using tf.garage.optimizer.adam, and I'm putting the learning rate as 0.01, and I'm using the 1000 epochs, and I'm now writing the iteration for 1000 epochs like this. And then with tf.gradient tape as type, I have already explained you, I'm calculating the loss as f underscore x, x comma y. This is basically I'm defining it as loss, this particular function. And then I'm using gradients is equal to tape.gradient loss, and then with respect to x and y I am calculating the loss. And then what I am doing now is I am actually using these gradients over here, and with the zip command with respect with x and y, what I am doing is I'm passing this information of gradients and the x and y variables in a zip format to apply underscore gradients. And what exactly it is doing is it is actually used within this optimizer function to calculate the gradient descent. So we know that if you remember the gradient descent, so what we do is we actually calculate the w new is equal to w old minus alpha times the derivative of the loss with respect to w old. So what exactly this particular piece of code is doing, really implementing the gradient descent, this one. So this is basically the idea. So we are actually using apply underscore gradients to calculate the gradient descent using the optimizer which we have defined over here, and then we are just printing these variables. So let me run this piece of code and see what is the minimum value that we obtain. So it is running for 1000 epochs, and the answer that it is generating is 0.66 and 0.66. So this is the minimum value that is recorded for this particular function when you do a minimization of this function and using the Adam optimizer. Another important aspect that I want to show you is that in this particular case, if you remember, I am using this particular loss. I'm calculating it with respect to x and with respect to the y when we are doing tape dot gradient. But the problem is I cannot use this multiple times, this particular piece of code. So if, let us say, you have these variables x and y, I am defining it as 2 and 1. So now I am not doing minimization of this function. What I am doing is simply calculating the derivative of the loss with respect to x and y. I am not doing minimization here. Please note, this particular exercise was to calculate the minimization of this function, but now this particular piece of code is to calculate the derivative of this function with respect to x and y and calculating the higher order derivatives. So the concern here is that if I use tape dot gradient loss with respect to x and y one time, and if I repeat that same story again, let us say like this, that is the higher order derivative I want to calculate, what I will do is I will call tape dot gradient, and then I will pass these two arguments here, and then I will pass x and y here. What I think is that it should calculate this particular thing derivative with respect to this, and it should calculate this particular thing with respect to this. So ideally it should be able to do the derivative calculation and should give you higher order derivatives with respect to x and with respect to y, but it is not the case. So let me run this, and you see what you get is this thing is okay, 3 and 2 is okay, but when you calculate these higher order derivatives, these answers are not right, what you are calculated over here. The problem is we cannot actually use cascading of these tape dot gradients in the same fashion as I was doing it here in this particular case. So that's why this thing is not valid. So in order to implement that same story like this one, if I want to calculate the higher order derivatives with respect to x and y, what I can do is I can actually use this particular piece of code to implement it. So let me run this particular piece of code. So what you get is the derivatives are correctly calculated. Here what I am doing is I am calculating the derivative of this particular loss with respect to x, then with respect to y, then with respect to then this is the higher order derivative, that is derivative of the loss with respect to x square, then this is the derivative of the loss with respect to xy, then we have derivative of the loss with respect to y square, then we have derivative of the loss with respect to yx. You can actually calculate yourself the mathematics behind it. It is very easy. So if you want, then I can actually show you one of them. Right now the function that we are using is this one. So if you have this, let us say call it as loss. So if I calculate the derivative of the loss with respect to x, it is actually 2x minus 1 plus y, and if I calculate the derivative of the loss with respect to x again, then what I will get is answer 2. And then if I calculate the derivative of the loss with respect to y, then what I will get is 2 times y minus 1 plus x. If I calculate the derivative of the loss with respect to y again, then what I will get is answer as 2. If you want to calculate the derivative of the loss with respect to x and then with respect to y, you try yourself what will be the answer, and then verify it with the results that you will get over here. So see 3 2 2 2 1 0. So this I have already calculated, so you can put these values over here. So if you put x as the initial value of x is 0 and this y is so the initial value of the x and y is 2 and 1. So if I put x as 2, so it will be 3. So this is the answer that you are getting over here, 3. In the similar way, if you put these values, you will get these derivatives answers. So this way you can actually calculate the higher order derivatives for any function. This is another way of implementing it. You can call this loss with respect to x and y once you call it in concatenation form like this, and then you can actually use separate gradients, but now you have to use persistent equal to true here. So this is the same as here also you are using persistent equal to true, because you are calling this gradients multiple times. So that is why this is actually required. Similarly for here also, you can do this. So you will get the same answers like this over here. So this finishes off with the idea of explaining you the gradient tapes and how to calculate the higher order derivatives. I hope you have understood it. So we will be actually using this particular idea of gradient tapes to implement some gradients during the backpropagation of neural networks and other architectures as well. And this is a problem statement for you. Like if you want to, this is a particular function, and if you want to calculate the gradients with respect to a, b, c and x, y, where a, b, c are the variables and x, y are the constants, this is I am leaving it as an exercise for you to perform, and let me know whether you have got the right answer or not. I will upload the answer to this particular problem statement in my GitHub repository. You can check that in my link posted in the description section. Thank you for watching my lecture. See you next time.